right, boys and girls, let's take a look at our first free response question. It's a calculator problem. We're given a table of values and a good old particle problem. So a particle moves along a straight line and its velocity in inches per second at various times in seconds is given by this table below. So the table on the left, not really consistent on what it goes up by. It goes up by 2, goes up by 3, goes up by 3, goes up by 2. Over here we're just given a bunch of ugly numbers, which is why it is a calculator problem. And so, here we are. We'll do A and B, and then C and D. We'll go back and forth between here and the calculator. But let's get started. Estimate V prime of 9. Now, V prime of 9 means if you were to take the derivative and plug in 9, what do you get? Oh, this is the regular old function, and there is no 9. So what I'm thinking is, okay, the derivative. Oh, so the derivative means slope. So if I'm going to estimate V prime of 9, why don't I estimate the slope between 8 and 10? Because 9 just so happens to be in the middle of that. So what we're going to do for part A is we're going to do V prime of 9 is going to be the slope formula connecting 8 and 10. So we'll do V of 10 minus V of 8, vegetable juice, over 10 minus 8. So we'll run to our calculator and find out what V of 10, let me see, V of 10 is 12.100 minus V of 8, which is 7.744 over 10 minus 8. We'll just throw all of that into a calculator, get some number, and we'll see what happens when we do just that. All right, let's plug stuff in. Big parentheses for the numerator, 12.100, which is just 12.1. Minus 7.744, so 7.744, close the parentheses, all divided by 10 minus 8. It's going to be 2, but we're just going to use our calculator anyway for just, showing you how to do stuff purposes. Hit enter, and you get, a nice 2.178, nothing to really round. So let's go back, write that out, and explain what that means in this context. Okay, so we ended up getting 2.178. Now, if we're given a particle moving at inches per second over time, right, the derivative of that is going to be inches per second squared. So the answer for A is going to be inches per second squared. Okay, and that's because it's the acceleration. When you take the derivative of the velocity, you're going to get acceleration. That's why we get the per second squared attachment. Now that's A. B is asking us to describe what the integral of V prime of t from 0 to 10 represents. The integral, right, between 0 and 10 of V prime of t. So I guess we'll do dt. Now what that gives us normally is we would say, okay, so that would just be like the capital V of 10 minus the capital V. But what that means here is if we're taking the integral of the derivative, we kind of go back to square one, which in this case is regular V of t. So this is going to end up being V of 10 minus V of 0. Right? And I don't need a calculator for this one. We already know V of 10 is 12.100, V of 0 is 0, and because I kind of can do the math in my head, I know I'm going to get 12.100. And since this is dealing with the original velocity, it's going to be inches per second. Okay? So the answer to A was acceleration. The answer to B was take the acceleration, integrate that, which takes you back to the original velocity. Fun, fun, fun in the sun. Now what we're going to do is we'll open up a new slide, okay, and we'll take a look at C and D on this slide and try to understand what they mean and see if we need our calculator for that. So C is asking us to use Riemann sums. Ooh, everybody loves that, with 4 subintervals to estimate the total distance traveled by the particle in the first 10 seconds. Left Riemann sums. Ugh. Okay, so the way you handle left Riemann sums is we're going to have 4 subintervals. Here we see like 5 chunks, which is kind of what we want because 4 subintervals means U to U, U to U, U to U, and U to U. So what we do is we take the length of the chunks, right? And we use this number because it's considered the left subinterval, right? We could draw ourselves a line, and I don't know what this picture is going to look like, so I'm not going to really lose a whole lot of sleep over it. But again, when you're using left Riemann sums, you're going to use whatever intervals you have and plug in the lower version of that. If it was the right Riemann sum, we plug in the upper version of it, and if it was mid-point Riemann sums, then we would just do the middle. That's not what we're dealing with here. So this interval is 2 minus 0, so we're doing problem C here. 2 minus 0, which is 2 units in length, and we're going to multiply the left side of it, which is going to be 0, plus the second interval is 5 minus 2, which is 3 units in length, and we're going to multiply the left side of it, which is 0.484. So we will want our calculator for this guy. The next interval is going to be 8 minus 5 units in length, so plus 3 parentheses. And we're going to multiply the left of it, so 3.025. And then the next one is 2 units in length, and we're going to multiply the left side of that, 7.744. So let's run to our calculator and see what happens when we type all of that in. Okay, 2 times 0, probably don't need to use that, but I did it anyway. The next one was 3 times 484, so 0.484, easy to memorize, that's a Pottstown area code from where I'm from, plus 3 times parentheses 3.025, and then the next one was 2 parentheses 7.744. It's going to be an underestimate. Oh, ooh, that was a close one. 7.744. Okay. Looks like no mistakes made. Thank goodness. 26.015. So let's go back, write that out, and try to explain what that means. All right, so the number we ended up with, 26.015, and since we're integrating the velocity function, the integral of the velocity function is the position function. So according to this, what this is telling us is we traveled a distance of 26.015 inches. Now, is that realistic? Is that really what's going to happen? No, because if we're using left Riemann sums, then we're probably underestimating our actual answer, but that's what we were asked to do here, and so that's what we did. Now D is asking us to use quadratic regression to find the equation of V of t. So we're going to take this table right here. We're going to do QuadReg in our TI-84 plus, and that will get us a formula. Once we get the formula, use the equation to find the actual distance traveled by the particle over the first 10 seconds. Show all the steps necessary. So not only are we writing out a formula, we're going to use that formula to find the actual distance traveled over the first 10 seconds. So here we go. Okay, this is how we do quadratic regression. So we're going to take the table, okay, and we're going to use all the numbers in the table. Go to Stat, go to Edit, and on the left side, type out the x, or in our case, the t values. So that was the left side of the table, 0, 2, 5, 8, 10. Okay? So let's move to the right, and we'll put in those numbers, which was 0 again, 0.484, 3.025, 7 that's a 1, 7.744, and 12.100, which is just going to be 12.1. So in this problem, right, if you remember, we were not just said, let's find the equation. We were asked to find the equation and then use that equation to do something else. Okay, so when we find, QuadReg, this is what we're going to do. Go to Stat, go to Calc, and QuadReg is number 5. So you can either hit 5 or go down to it. Great. Now, since we're not only going to write out this formula, we're also going to use this formula. We're going to store this in our calculator, so when we use the formula, it's going to be there waiting for us. So store reg EQ, hit enter. Oh, nope, I'm sorry. Go to vars, yvars, enter, enter. Okay, go to vars, yvars, enter, enter. And this will store our equation into y equals. Go down to calculate, hit enter, and there's our equation. It's actually really pleasant. And what we'll do is we'll hold on to it, we'll save it, and then we'll write it down so we don't have to go back and then come back and then go back and then come back. So the equation in this case is just going to be y equals 0.121x squared. That's it. Now, here it is waiting for us when we hit y equals. Now, is it exact? No, because TI likes to always make it different. But part 2 of this was asking for us to find the distance traveled for the first 10 seconds. So we're going to use our calculator to do this. Now, this is our velocity function. This is the velocity answer that we got. So in order to find the total distance traveled for the first 10 seconds, we're going to integrate. So we do that by using our calculator and hitting second trace, which takes us to calc. 7 is the integral. So go down to 7, you get a nice little parabola, which makes sense, and we're going to set our lower limit, since we're doing the first 10 seconds, our lower limit will be between 0, and our upper limit will be 10, and that's going to give us an answer of 40.33333333333333. So let's go back, let's write down all the information that we came up with, and try to explain what all of that means. All right, so let's finish this guy out. All right, we're on D, and the equation that we ended up with was, if we're doing the velocity function, QuadReg gave us v of t equals 0.121 t squared plus 0t plus 0, so this is part 1 of that problem. Okay, that's the equation that we came up with. Now, in order to use that to find the actual distance traveled using our calculator, we decided that we would integrate that velocity function, which gives us distance. So between 0 and 10 of the velocity function, dt, ended up giving us 40.33333, which means we actually traveled a distance of 40.3 repeating inches. Now, what we had up here was a complete underestimate, which usually happens, not always, but usually happens with left Riemann sum intervals, because you're not looking for perfection, you're looking for drawing rectangles and blah, 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 blah. But this is the actual distance traveled according to this information. And this is the underestimate. So yeah, that's part 1, or problem 1 of our free response question here in the ultimate GOAT, whatever I'm calling this thing. So more to come. 4 of them, 5 of them. Ugh. Thanks for watching, like, and subscribe.